All right. This is the Lecture 2 supplementary video. I will be talking about the other weird case that I mentioned during lecture I call it the grit method, but it's a repeated use of integration by parts. And then after that, I'm going to talk about 7.3, which is trig sub. Hopefully, I'll be able to get through all three examples, but if not, I'll ask Gina to do one of the examples just for time's sake during recitation. All right, so let's start with integration by parts. If you guys remember, the grid method. If you guys remember integration by parts, right? It's the ultraviolet minus integral of voodoo, and it comes from two functions being multiplied to each other, right? A u and a v prime, and if we can identify the u and the v prime, then we can kind of rewrite it, yada yada yada. However, sometimes, no matter what the two functions are, you're gonna run into, I guess, trouble. So let me just jump right into the example here. So let's say I have this in my integrand, e to the x times cosine of x, and you look at that and you're like, can I do u sub on this? And you're like, no, I don't think I can, right? If I derive e to the x, that doesn't appear in my integral. If I derive cosine of x, that doesn't appear in my integral as well. So u sub's at the window. It's a product of two things. So you're like, okay, I'm thinking this might be integration by parts. However, if you do integration by parts and you run the whole Lipet thing that we talked about in class, right, the order on how to choose u, you're going to find that u is going to be e to the x, du should be e to the x dx, and then dv is going to equal cosine of x dx, and then v is going to equal sine of x, right? And when you run integration by parts on this, you're actually going to find out that it's not going to make your integrand any simpler. Watch. Right, so this is equal to this. So if I run this, uv is equal to e to the x sine of x minus the integral of v sine of x du, which is e to the x and then a dx, right? And if you look at this thing, and you compare it to how you started, you're thinking, this isn't much simpler than what I started with. So what do? Do you throw in the towel? Do you give up? This is why I call this the grit method, because you say, no, I don't give up. I'm going to keep going, and I'm going to try integration by parts again, even though it doesn't look like it's going to help, right? So that's why I like calling this grit method, because you got to push through sometimes, and you'll get to the answer, I promise. Watch. If I set, once again, sometimes some people switch up the letters. Instead of using UV again, they'll use, like, what are the next ones? Like W and, oh wait, you can't use that one. Like, I don't know, L and M or whatever, two other ones. I'm just going to use the same letters, all right? So U, once again, is going to be e to the x. Du is equal to e to the x dx. dv is sine x this time. And v is negative cosine x. Let me just double check that. Yeah, right? So let's see what happens. Let's run integration by parts one more time. Well, this first piece, just nothing happened to it, so it's just going to stay e to the x sine of x, right? Minus, you're now subtracting a new integration by parts. So I'm going to put a bracket here because this is going to have two more terms. It's going to have another ultraviolet minus integral of voodoo. You guys see that, right? So ultraviolet it's a new ultraviolet. It's not the ultraviolet from the first round, right? It's this new UV definition. So it goes e to the x times negative cosine x. So negative cosine x. Please watch out for your negatives, okay? Minus the integral of voodoo. So once again, v is negative cosine x. I'll put that positive here, cosine x. And then the du is an e to the x dx. Now, I know what some of you are thinking. You're like, wait, that didn't help, right? It's like, that's not any easier to John, did you lead us down a rabbit hole for no reason? Just hang on, man. Just hang on, right? Let's rewrite this. What's going to happen? E to the x sine of x. I'm going to distribute this negative. It becomes plus e to the x cosine x minus integral of e to the x cosine x dx. Once again, please keep it a good eye, like a watchful eye on your on your negatives and positives, okay? Now, I know you guys are looking at this and you're like, yeah, that didn't help. You just flipped the signs, Joe. What are you doing, right? Hold on. If you think about it, this whole thing, what is this all equal to? Well, let me go back. What was this all equal to? Oh yeah, that's right. It was equal to the original problem, right? E to the x cosine x. Let me rewrite the original problem here on the left side. Integral of e to the x cosine x dx. And you're like, wait a minute. I've seen that before. I've seen this e to the x cos x dx, the integral. Oh my gosh. No. Is he going to do it? I think he's going to do it. Watch what happens. I can add this bad boy to both sides of this equation. Algebra? No. Oh yes. You're allowed to do this. What are you left with? On the right side, it goes away. Our problems are solved. It cancels out. On the left side, well, there's one of these, and then there's another one of these. So that means there's two of them when you add them together. Oh, snap. I gotta write all this stuff now. Hold on. E to the x, cosine x, right? The last thing we gotta do is, well, the question asked for this piece, right? Integral of e to the x cosine x. So what do you think we're gonna do? We're going to get rid of that 2 by dividing everything by 2. And since we are technically integrating, right, we need a plus c at the end. And that's it. That's the answer. You can clean it up a little bit. E to the x over 2 sine of x plus e to the x over 2 cosine of x plus c. This is it. We did it. We solved the integral by pushing through, even though the chips were down and life told us that things were too. All right, I'm too tired for that. All right, so yes, all right, that's it. That's the grit method, right? Essentially, what you're looking for is your original problem to reappear in your work, and that's why with grit method, it's usually used. The grid method is usually used when dealing with an exponential function and a trig function, when those two things are being multiplied to each other, right? It's the e and t in Lipet, right? And the reason why that is because think about it, right? Sine and cosine, they are what's called cyclic. You guys don't need to know what that means, but sine and cosine are cyclic, meaning when you derive them or integrate them, you'll eventually get back to where you started, right? And that happened in this case, right? We started with a cosine, it turned into a sine, and then when we used integration by parts again, it turned into cosine again. So when you have a trig and an exponential, yeah, it's most likely going to be a grit method problem. You're going to see it reappear in your work, and then all you have to do is this trick where you just add the original problem to both sides and divide through by a constant. All right, so that's the grit method in a nutshell. Gina will go through tabular method, which is another fun case. Tabular is more fun. Everyone loves tabular with you guys. And yeah, so I'm just going to jump straight to 7.3. We're moving right along here. 7.3 is on trig sub. And it should sound familiar, right? Because it's like you think of like u sub when you hear trig, like when it's like something sub. It's similar. It's another method on how to change the way an integral looks. 1 second. All right, so trig sub boils down to 3 cases. All right, I'm gonna write down the 3 cases here. I'm gonna go through all 3. Hopefully. If by 2 the time is too long, I'll ask Gina to do the last one during a recitation. But yeah, it boils down to 3 cases. All right. So the first one looks like this: when you have a constant squared minus x squared. The second case is when you have x squared plus a constant squared, right? Or a squared plus x squared, because right, that doesn't matter. And then the third case is when you have the square root of x squared minus a squared. Now, the reason why these are so peculiar and why it's related to trig, you got to think back to your trig identities. I hope you guys remember what they are. Do you remember your trig identities? Identities. They were, one of them was like sine squared theta plus cos squared theta is equal to 1. I think the other one was like tangent squared of theta plus 1 is equal to secant squared. These will come back. These come back exactly here with the trig sub. All right, and you're going to see how it works out in each case. All right, but as long as you can identify what form they're in, right, out of these three cases, you should be able to use one of these trig identities and kind of like make your substitution accordingly. I know that sounds very cryptic, but hopefully the example will make sense. So let's look at this first example. Call it example 1. We're integrating 1 over integral of 1 minus x squared dx. Now, some of you may look at this and be like, wait, that looks kind of familiar. I think I know that one, right? If you guys remember from hopefully Calc AB or BC, you guys learned that the derivative of the inverse of sine is actually equal to 1 over root 1 minus x squared, right? The derivative of cos inverse is like the same thing, but it's negative. And then the derivative of tan inverse is 1 over 1 plus x squared, right? So hopefully you guys remember that. But we're going to show this using trig substitution. All right? So watch. Here we go. How do we do trig substitution? Well, first you got to identify which case does this fall under, right? So the first thing you want to figure out is what case is this? Right? If you look at it, well, it looks like it falls under the first case because we have a constant squared. Well, let me do this in different color. Constant squared minus your x squared, right? Where a is going to equal 1, right? Because 1 squared is just 1. So thank goodness it's a perfect square. So yeah, it looks like it falls under case 1. Well, what happens under case 1? We have to think... sorry, hold on. Sorry about that. We have to recall our trig identities, right? So we know that, what is it? Sine squared theta plus cos squared theta is equal to 1. Well, if you like look at this, right, and I just kind of like move the cosine over to the other side, I get sine squared of theta is equal to 1 minus cos squared theta. Right? And then, and you guys can kind of see, right? It kind of resembles, like, it kind of like matches up here, right? Like the 1 could represent the a, and then like the cosine squared can represent the x squared. So once you identify which case it falls under, right? You actually can make the substitution right away. So I'm just gonna tell you guys here, when you see case number 1, let x equal a times sine theta. That a is pretty important because it's not always going to be 1, right? It could be another perfect square or it can be an imperfect square. So just watch out for that. So when you see case 1, it's going to be a sine theta. When you see case 2, it's going to be a tan theta. And then because, you know, I don't know if you guys can see it, tangent squared plus 1 is secant squared, right? And then x equals a secant theta for the third case. All right, and hopefully through the examples it'll make more sense. So watch. We're in the first case, so we're gonna let x equal a sine theta, or in this case it's gonna be just sine theta. So what happens now? Well, I can rewrite integral of 1 over root 1 minus sine squared theta. Now, I can't keep that dx in there. I need to solve for dx because I have a function in terms of theta. You guys see that, right? I can't have conflicting variables in my integral. That's not allowed. You go to MathGL for that, right? So I need a way to find dx. Well, if I have x, then I can figure out what dx is, right? In terms of theta. It's going to be cosine theta. So what am I left with? How do I solve for dx? Well, I'm going to just multiply both sides by d theta, and I get dx equals cos theta d theta. So hopefully you guys see, right? So now I can do the old switcheroo. I can replace the dx with cos theta d theta. So I'm going to do that right here. Cos theta. d theta. Now I have a d theta, so I can integrate it properly, and I have this extra cosine flying around. And if anything, this should kind of be reminiscent of u sub, because this is very similar to u sub, right? When you have to du dx, and then like you got to solve for the dx. I don't know how you guys learned u sub, but this is essentially, it's very similar to u sub. So let's see what happens here. The integral of, I'm going to clean this up a little bit, cosine theta. There's a d theta on the outside. On the bottom, what do you see? You see 1 minus sine squared theta. And you're like, wait a minute. Wait, he said something about that in the past, right? He said something about that up here, right? Oh yeah, our trig identities. I know that 1 minus sine squared theta is actually equal to cosine squared of theta. I know, right? And hopefully now this kind of makes sense. Why we needed to make the substitution the way we did. It's because of that pesky square root. That square root is going to mesh nicely with this cosine squared. Right? You guys see that? It's going to simplify down, and you're left with cosine squared. I guess I didn't need to write this stuff down, but you're left with 1 d theta. Now, look at this. 1 d theta compared to this original problem. Right? I don't know why I didn't include the dx. This original problem. Which one looks more complicated? Right? You look at this original problem, you're like, I don't know how to integrate that. But then you look at this one, you're like, oh, I know how to integrate that. Ah, there's that theme again, right? Rewriting the integral into something that we can integrate. All right, I'll stop. How do I integrate this? Well, my variable's theta, so it looks like if I'm doing a reverse power rule, I'm just left with theta plus a c. And I know you want to think that you're done. I know you want to believe that you're done, but you're actually not done at this part. Why? Look at the original problem. What variable is my original problem in terms of? Right? I feel like Dora the Explorer asking you guys through the screen. It's in terms of x. Well, if I give you a problem in terms of x, your answer needs to be in terms of x. So the very last step is you need to turn this back in terms of x. Well, how do we do that? I have a theta here. If I go back to the original substitution, that should help me convert back to x, right? So we said x was equal to sine theta. Yeah? If x is equal to sine theta, well then I can just do, can't I inverse sine both sides? And I'm left with inverse sine of x is equal to theta, and oh my gosh, you're telling me I can replace that theta with sine inverse. Ah, that's where it comes from. Cool. So cool, right? We called it in the beginning too, right? We said because we know the derivative of sine inverse, right? Hopefully. But yeah, that's where it comes from. So that's trig sub in a nutshell. I'll be honest, this last step can sometimes get a little tricky. I am going to do one more example. I highly recommend you watch this one as well, because it's an example where after you do the trig sub, it gets tricky at the end. And then the last one I'm gonna leave up to Gina to do in recitation. All right. So what example is this? This is example whatever. I called it example 1. Let's call this example 2. So let's look at another case. So this one's gonna be a different case. I forgot to say that first example was on page 432 in the PDF of the book. So if you guys want to check that out, it's up there. It's example 1 in that section, actually. This next one is it's example 4 on page 433. I'm just going to work through it. And yeah, so if you guys need a reference, you can look at the book too. So once again, we have an integral, and we're looking at this thing, and you're like, oh snap. I don't know how to integrate that. I can't use u sub, and I can't use integration by parts. So do I give up? No. The way you know that this is a trig sub is, once again, you got to look at the form and see if it falls under any of the cases, right? If you guys see here, I have x squared plus a squared, right? If 9 is a squared, then this implies that a is equal to 3. So this actually is going to work out, right? And I wrote it up here already, somewhere. Yeah, it's the second case, right? We're going to let, for this problem, we're going to let x equals a tan theta, a tangent of theta, All right, and you're going to see why, because once again, it follows the tangent squared theta plus 1 is equal to secant. But you're going to see that very soon, right? So in this case, x is equal to not 9 tan theta, but 3 tan theta. Watch out for that, okay? Which means dx is equal to 3 times, what's the derivative of tangent? It's secant squared theta. And I need that d theta at the end. So we have everything we need here. We're going to make this trig substitution now. Right, so I don't think I numbered it last time, but this is the first step, choose wisely. Second step is make the substitution and integrate. So let's make the substitution. It's 1 over root, it's not x anymore, it's 3 tan theta quantity squared plus 9. And it's not dx anymore, right? It's not dx. dx becomes 3 secant squared theta d theta. So this one's going to get a little hairier, all right? But in all of these problems, all right, something beautiful should always happen. Some really, really nice cancellation should happen in these problems. Watch. Let's simplify. What does this become? This becomes 9 tan squared theta plus 9. It's still under the root, right? And let's see. Oh, I can factor out a 9, right? I get 9 times tan squared theta plus 1, all under the root still. And if you guys remember, right, with roots, it's like being raised to the 1/2 power. So what is this? This is actually 3 square root secant squared theta. You see what I did there? I made the not the substitution. I made I used the trig identity. Tan squared of theta plus 1 is equal to secant squared. And then, so what does this mean? This means I have a 3 on the bottom. I'll do some blue. I have a 3 on bottom. I have a 3 on top. I have a square root of secant squared and a secant squared. Do you guys see what's going to happen? If I rewrite this, some beautiful, beautiful, beautiful cancellation happens here, right? 3's are going to cancel out. And you're left with the integral of secant theta d theta. Right? Isn't that much easier to whatchamacallit, to play with than the original problem? Some of you are looking at it and probably like, wait, I don't know what the integral of secant theta is. It's okay. It's all right. It was one of those things that you do need to know. They do teach you it in AV. But if you don't know, the integral of secant theta is ln of absolute value secant theta plus tan theta. All right. And that's the end of step 2, right? Make the substitution and integrate. The third is convert back to x, in terms of x. Because once again, we don't want our problem to end up in a different variable than what we started with. It's kind of rude, you know? So we don't want to be rude, so we got to convert this back to in terms of x. Well, how do we do this? Well, we do this something similar to what we did in the first example, except it's going to be a little bit weirder now. X, we said, was equal to 3 tangent of theta, right? Just want to double check here. 3 tangent, yep. All right, so what this means is, if our final answer is ln of secant theta plus tan theta plus c, I got to get rid of these secant theta, tan theta. We don't want them, right? We need everything in terms of x. So here's the trick. The trick goes like this. I'm going to first rewrite this as x over 3 is equal to tan theta. Why? Because I can use what I know about right triangles to come up with... Oh, that is such an ugly triangle. I'm sorry, guys. I can use what I know about right triangles, right? And if I call this theta, to figure out what secant is in terms of the triangle, in terms of x, right? So once again, we know what tangent theta is, right? It's x over 3. So we can actually just put that in right now. That's x over 3. But we got to know, what is secant theta? Well, let's solve this triangle here. If tangent of theta, if you guys remember SOHCAHTOA, if tangent of theta is equal to opposite over adjacent, then in this triangle, the opposite from theta is x, adjacent is 3. And using Pythagorean's theorem, it becomes x squared plus 9 is your hypotenuse. Why do we need that? Well, we got to figure out secant of theta. Hopefully you guys know what secant of theta is, 1 over cosine of theta. So it's like cosine of theta, but you flip it. So instead of so ka toa, or instead of ka, it's like, wait. Yeah, instead of ka, it's like a over h. It's like adjacent over hypotenuse. Is that right? Nope. A over h is cosine. It's h over a. There you go. It's h over a. Hopefully you guys know what I'm talking about, right? So ka toa. This is your sine, cosine, tangent, right? But then secant is equal to 1 over cosine. So that's going to be h over. Yeah, I just wanted to make sure. Yes, it's h over a. All right, so this means we need the hypotenuse, which is what we found in our triangle. It's x squared plus 9 over adjacent, which is 3. Woo! So what does that mean? This thing, x squared plus 9 over 3, is equal to secant theta. We make one last substitution into our very, very ugly answer here, and we are done. That's it for trig sub. That's the second case for trig sub, right? Just make sure your final answers are in terms of x, and you'll be good. The last case, though, all right, it's very, very similar. You're just gonna have to make a substitution. You're gonna have to simplify some stuff. Some stuff's gonna cancel out very, very nicely, and then at the end, make sure your final answer, after you integrate, make sure your final answer is in terms of x, right? I'm going to tell Gina to go through example 5 with you guys during recitation in, I think it's page 434. If you guys want to do it yourself, you can, but yeah. All right, so hopefully this helps. How far did I do? Oh my gosh, 20-something minutes. Please reach out if you have questions, guys, and best of luck. All right, I'll see you guys.